Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you, and this is welcome to this DADM 3 course under NPTEL MOOC series. And as you know, this course is spread over 12 weeks, total number of lectures is 60 and the total number of contact hours is 30, which means that each lecture is for half an hour and each week we have 5 lectures of half an hour each. And after each week of lectures of 5 number, you basically take an assignment, and after the 12 assignments you basically will be appearing for the final examination. And my good name is Raghunandan Sengupta from the IME department, IIT Kanpur. And as you can see in the slide, we are on the 59th lecture, which is the last but one lecture, and we are in the 12th week. And the 50th lecture was basically dealing with the concept that how the modelings would basically be done. And if you remember the concept of modeling, I had been mentioning time and again in the first few classes of 1 or 2 weeks, that the methodologies concept, how you solve, would be the main emphasis of this course, but how you model, how you consider the constraints would be an important point, which will only come through lot of experience, lot of problem solving, lot of practical analysis. And then in the last slide or last 2 slides, we consider the concept of robustness and how robustness was important, and how robustness and sensitivity analysis are some concept which basically give you the same idea that what you want to basically propose or want to find out. So, with this we will start the 59th lecture and basically discuss more about the robustness part, and again I will discuss some models, their proofs, their the datas, the pre-processing part, and what are the answers and how we can analyze them. So, considering robustness, the salient points are, so we can consider the constraints are robust, that means the corresponding the fact that there would be a probability based on which we can say constraint 1 or 2 or 3, whatever it is greater than some fixed value or a changing value also, with some level of reliability, some level of robustness, and those level of robustness or reliabilities, I am going to use the word reliability and robustness interchangeably. So, please bear with me. They would be given by the level given by beta 1. And this level of beta 1 and beta 2 would have same implication as we discussed in the diagrammatic form when we considered reliability, when we consider the PMA approach and the RIA approach, where if you remember, in consider separately, in one case the circle slowly started increasing till it was tangent to the feasible region, and the size of that value of the radius was beta. In another case, you kept beta fixed and you basically shifted the feasible region more inside such that it was tangent to the circle. Why circle? Because we are considering that when you basically convert from the x space to the u space, considering the univariate normal and all of them are orthogonal, you will basically have a circle in the 2-dimensional case. In the higher dimension, it will be a sphere and so on and so forth, and it will be a hypersphere corresponding to the higher dimensions. So, coming to the robustness part, so the constraints can be robust, and you can consider the robustness by considering the concept of betas. You can also consider the objective functions to be robust, but in our discussion on the problems we will be solving, we will only consider the concept of constraints to be robust and basically give the solutions accordingly. The robust counterpart for these nominal problems. So, now here how we will solve or how we will basically propose the model would be, obviously there is a deterministic part of the problem. We will convert the deterministic one in the probabilistic part, in the sense the corresponding probability with the level of reliability of beta 1 to beta 2 or beta 3, beta 4, depending on number of constraints which we have, would be considered in the constraints, and then this transformed form, which is the probabilistic constraints, would basically be solved using the robust counterpart. So, the first part where the deterministic models would not be written, we will immediately write the probabilistic counterpart of those deterministic model and then give an idea. Initially we will give an idea how the problems can be solved, and we will write their robust counterpart, and then basically skip the simulation part, because simulation would basically more of trying to basically build the codes in MATLAB or whatever it is. I will just give you the gist and then go into the data which is utilized, how the pre-processed data is analyzed, and how we basically utilize the pre-processed data in the model formulation, model solving, and then give the results and try to analyze the results. That is also very important. So, we can use the concept of uncertainty sets. So, the uncertainty sets would basically mean a set of values where the corresponding probabilities would be there. Probabilities would not be considered per se, the probabilities or the chances would be there that each values in the uncertain set would basically have a certain probability of that being true or that being picked up. And we will basically have a set of the uncertainty level of this set. So, each value which is appearing would basically have a probability which I mentioned, and these uncertainty sets would basically be considered, in our example we consider in such a way that we will basically consider a nominal value, and that is nominal value would be the so called expected value over and above below which that actual value would be perturbed or changed, and that perturbation and change would basically be considered as the level of reliability in the robust counterpart sense. You will use this set in place of the nominal data. Nominal data would basically, as I mentioned just few minutes back, would be the average value, and we will basically use this nominal data to generate the robust counterpart. Now, one of the main important difference between the reliability part or concept or the stochastic concept and the robust concept is, in the reliability part we would or we have considered the concept of some particular distribution per se, but in the robust counterpart we would not be considering. But now, later on you will see, and obviously there would be a question from your part, that we will be using some nominal values over and below which the perturbation would be true. So, these nominal values will be considering based on the fact that we have the information or we have the practical knowledge that the returns of the scripts or the returns of the portfolio would be extreme value distribution. So, we will utilize the concept of expected value of the EVDs in order to basically find out what is the nominal value over and below which the perturbations would be true. We will use the concept of ellipsoidal sets, and the concept of linear constraints in the nominal problem may become nonlinear. So, but obviously we will try to check that when it becomes nonlinear, the concept of convexity should be true, or else the concept of optimization would not be able to be utilized in trying to solve the problem. Now, in general, robustness, as I said, in the uncertainty sets, there are different ways to basically model the uncertainty sets. So, in general we consider the uncertainty sets given by U, where the realized values would be given from A1 to AK, and obviously each of them would have some level of reliability or probability. In the interval uncertainty sets, we will consider the value of the fluctuation and the value of perturbations of the parameter A, or it can be X, it can be W, whatever it is. The parameter A would basically fluctuate between a minimum value L and a maximum value of U. For each and every A, there would be a L1, L2, L3 till Lk, considering there are values A1 to Ak. Corresponding to A1 to Ak, the upper bound would be given by small u1 to small uk. And the ellipsoidal uncertainty sets would be considered based on the fact that we will consider in a very simple sense, if it is a 2-dimension one, it will basically be a circle, and the center of the circle would be the nominal value over and below which the perturbation set would be. So, if it is the level of variances, I am bringing the concept of variances, why I will come to that later on. If we consider the level of variances of the perturbations for both of these variables are to be of the equal value, then it will obviously it will be a circle. In the case if the variances are different, in that case we will basically have ellipsoid with a major and a minor axis in different direction depending on where the variance is high or where the perturbation is high. Perturbation is considered is like a atom which is fluctuating. Higher the level of energy, more the fluctuation is, and lower the energy, less the fluctuation is. So, if you are trying to find out the common area, it will be an ellipse or ellipsoid depending on which direction the perturbation or the movement or the vibration is high. Now, we will consider this ellipsoidal uncertain sets will be considered based on the fact that we are going to consider the L2 norm. Now, this concept of L2 norm I have discussed that in DADM 2 when we are discussing the concept of Electra and Topsis methods. So, this L1 norm, L2 norm till L infinity norms are the norms based on which we measure, and L2 norm is basically the concept of, in very simply we use in the Cartesian coordinate, where in order to find out the distances between 2 points, we basically find out x1 minus x2 whole square plus y1 minus y2 whole square, and then find out the square root of that, consider is in a 2-dimensional one. In a 3-dimensional one, it will basically be calculated accordingly. So, we will consider, and this norm of L2 norm has also been utilized in the case of reliability. If you remember in the PMA and RIA method, the constraint on the objective function depending on which problem formulation you are doing, whether the PMA or the RIA, we consider this norm of distance which was given by the distance norm, which is here, which I have just circled. So, that the distance norm is basically less than or equal to 1, because we are considering a unit circle. In the scenario generation method, here one may formulate the uncertainty sets, and obviously the general concept which we will use will be the interval set or the ellipsoidal sets, whatever all the other methods we consider. So, we will formulate the uncertainty sets that contain a finite number of scenarios as we generate them, and they are generated from a possible value of the parameters, and the parameter values A, that is the uncertainty set, would be denoted between by a set U and the level of realized values for the uncertainty set. So, the A value would basically take any of the values between A1 to AK depending on the level of probability or level of reliability which is true for those. So, realization of A1, A2, A3 would depend on the level of reliability which is there or which you want to assign to those uncertainty sets. Now, these are just for information, need not be too much bothered into going into these books or the papers, provided if you are interested to go into the research, it may be helpful. So, Benthal and Nemirovsky's, they are considered a very well known figure, and Bertimus and Sim are also considered stalwarts in trying to basically model the concept of robustness using the uncertainties level sets or the ellipsoidal sets concepts. So, their paper and their book came out in the years 1998, and after that in 2004 also there are seminal work by them, and they have described the different methods to construct these uncertainty sets. Now, the second point is important for our discussion here. Goldfrapp and Iyengar have shown that the confidence regions generated for parameters involved in equities portfolios, in trying to basically model the portfolio optimization, we consider the concept of ellipsoidal sets. So, the reason why we are mentioning that second point is that we will be discussing many of the problems from the portfolio optimization point of view. That is why we wanted to give you the reference that why we are going to consider the concept of ellipsoidal sets in order to model the portfolio optimization problem. So, let me continue reading it. So, they have shown that the confidence region generated for parameters involved in equities portfolios are ellipsoidal sets, and they advocate that their use in robust portfolio selections as uncertain sets are the best way how we can solve them. Now, in case of our methodology of solving would be consider this box and ball plot. In the box plot we consider the L infinity norm, and in the ball plot we consider the L2 norm, and we will consider the transformation being done in such a way we will consider the standard normal deviate, this concept of U set as we did in the reliability sense, that transforming from the X space to the U space would also be utilized here. So, usually this type of robust counterparts, once we basically have the probability, convert using the concept of box and ball into the robust counterpart, find out the commonality of the intersection between them, and then basically solve this problem accordingly. usually this type of robust counterparts comes under the category of second order cone programming problem. So, our Ball uncertainty is in the form of Lorentz cone. So, Lorentz cone is considered ice cream. So, if you have a cone, a set of an ice cream or the softy cone we consider, so they would basically be of the second order cone programming, and the order of the solution would be the quadratic, in order to basically give us an idea that why we are using the concept of quadratic programming is that because you remember the concept of variance would be coming time and again, and variance is basically coming from the fact that we are considering the second moment. So, the first moment was basically related to the mean value, second moment is basically related to the variances. So, our Ball uncertainty would be in the form of the Lorentz cone, and the Lorentz cone would be given if you remember. So, if we will basically the main part for the Lorentz cone to be true would be that the sum of the squares of all the i's, I is equal to 1 to m minus 1, if I basically add them and find out the square root, that should be less than equal to the mth one x m. X m is basically the dimension, not the dimension part, is basically the measure which we are doing in the mth dimension. So, we will basically have the concept utilized here. Now, this has something to do with, if you remember that if for a triangle to be true, that the sum of the two sides would be always be greater than the length of the third side, or else the triangle would not be formed. So, this is some concept which we try to utilize in the Lorentz cone, considering the L2 norm in a quadratic programming concept. So, since it is a second order problem, we will call them the quadratic constraint quadratic optimization, and this quadratic optimization will be utilized based on the fact that it will be a matrix Q if it is in a higher dimension, and the property, if you remember, of which I mentioned, the positive definite, positive semi definite, all this would basically hold true, such that we are able to solve the problems accordingly utilizing the robust counterpart. Earlier robust formulations has been solved by the Soester's model, Benthal and Nevirovsky's model, but they lack three basic requirements to give a better results. So, that means what are the requirements which are lacking? They do not consider for variance as a constraint, as it increases computational complexity of the model by making it a semi definite programming, because the more complexity you want to bring, obviously the answers will be more near to practicality, but it will basically increase the solution methodology, it will make much more difficult for us to solve. If the variance of the portfolio, but also remember that we have to basically consider the concept of the variance of the portfolio to be incorporated in our model, because we are trying to basically balance between the return, which is the first moment, and the risk, which is the second moment. If the variance of the portfolio is to be considered and computed, correlation and coefficients of all the assets cannot be 0 as considered by Bertimus in his work. Hence, variance covariance matrix might be utilized, which is basically the principal diagonal. Obviously, you know, but I will still repeat. The principal diagonal are the variances of the first to itself, the 2,2 element is the variance of the second to itself, and so on and so forth, and of the diagonal element are basically the covariances. Both box and ball uncertainty must be utilized to create the robust counterpart, and we will take basically the intersection of that with the common area. Based on that, we will solve and try to basically formulate the probability constraints into a robust counterpart and then solve them. First, we will basically have the nominon problem to be constructed. So, remember the nominon problem would be based on the fact that we will take the expected value or the mean value of them, and then basically try to model the problems according to the perturbations which we will have for over and below the nominal value. So, it is the problem which has an objective function which needs to be achieved adhering to some constraints. So, those constraints, in the case if they are deterministic, we will solve them using the deterministic method. If they are not, then obviously we will have the probabilistic counterpart. All the uncertain parameters variables are then identified. So, you have to basically first identify the variables and then model them as the constraints. Those uncertain parameters and the variables are then converted into uncertain sets as described above. So, first so what we have skipped here, I did mention that we will basically have the probabilistic constraint, convert this probabilistic constraint in the robust counterpart and then proceed. So, and using the concept of uncertainty sets for each and every of this robust or this perturbations values for each and every variable which you are going to consider. These uncertain sets are then put into the original nominal model to form a robust counterpart, just as I just mentioned. In our case, the resultant optimization problem becomes a semi-definite programming, considering that we are trying to consider variances, which are NP hard problems and unsolvable by basically interior point algorithm. So, obviously, you have to use either heuristic methods in order to get near optimum solutions. So, we will basically utilize some concept of very simple engineering in order to solve them. Now, we will consider one by one 4 models and also give their, where as necessary we will give their robust counterpart. So, in the robustness part in model 1, which consists containing probability. So, the first problem is like this: we have the return on the portfolio RP, we have the variance of the portfolio sigma square B, and we want to basically formulate the problem in such a way that we want to basically maximize a convex combination of the return and the risk. So, if lambda is high, it will basically put more weightage. If you are concentrating on the objective function, if lambda is high, we will put more weightages to the return. If lambda is low, we will put more weightage on the variances. Now, why we are maximizing? We are maximizing and trying to basically pull up the expected value, and maximizing a negative value, which basically we are trying to basically pull down that value, which is the variances. The second and the third constraints are very simple. I will still give me some time to repeat it. So, if you considering inside the bracket, what you have is basically the return on the portfolio is greater than some value of RP, which you have set for ourselves. The second constraint, again if you consider only the part which is inside the bracket, it means the double summation of xi, xj, sigma I, sigma j and rho ij basically means we have the variance covariances of each and every portfolio script, that is less than equal to sigma square p, which we have set for ourselves for the problem based on the level of confidence which the investor has. And the last constraint is basically related to the fact that the sum of the weights of xi's, xi's are the weights is equal to 1. Interestingly, we have considered the values of xi is greater than 0. So, here obviously we have not written it, but it should be that the values of xi's are between 0 and 1. Now, this would basically be the, when I have not mentioned probability, this is basically the simple deterministic part. The moment we bring in equation 1.1 and 1.2 as written in the slide the concept of probability, then we have basically converting this deterministic problem into the probabilistic sense. Now, and obviously on the right hand side we have the probabilities of the returns being greater than RP is greater than equal to beta 1, where beta 1 is the level of probability corresponding to the first constraint. And in the second constraint, the probability of the covariance of the portfolio being less than equal to sigma square p with some set value depending on the market conditions, that overall probability is greater than equal to beta 2. It means basically that the level of confidence which we are putting for the second constraint is greater than equal to some value of beta 2 or the beta 2 value which we have set for ourselves. What we will do is that what I have mentioned is that convert the first constraint using the nominal values and the different concept of ellipsoidal set into a robust counterpart, then convert the second constraint again depending on the level of robustness and the nominal values into the second robust counterpart. Now, what we consider as the nominal value in the first case and the second case. In the first case, we will consider the mean values of each every stocks Ri's which are there. So, we will basically collect the data, find out the expected value and basically consider the nominal values or the mean values for each and every stock. And in the second constraint, we will consider the variances and find out the average variances based on which we will try to basically find out, consider them as the nominal values, and based on that we will basically find out the counterpart for the second constraint. And obviously, as I mentioned that we are not going to consider any level of robustness in the objective function. The objective function here comprises, I will just read it, I have already mentioned that, but still I am reading it. The objective function of this model comprises of two parts. The first, which ensures the maximization of the return on the portfolio, while the second is the variance of the portfolio, which is to be minimized. So, as I mentioned, maximization of lambda into RP minus of 1 minus lambda into sigma square p basically means that I am trying to basically increase the first moment of the return of the portfolio and decrease the second moment, which is the variance of the portfolio. The first constraint denotes, as I said, that the actual return on the portfolio is greater than the threshold value RP with a level of probability or reliability beta 1. The second constraint implies that the actual variance of the portfolio is less than the threshold value with a level of probability of beta 2. And this beta 1 and beta 2, I am again repeating, depends on the investor. The third constraint implies that the sum of all the investment should be 1, along with the fact that no short selling is allowed. Here, if you remember, I mentioned the word, these are very interesting in the sense, if they are between 0 and x, it means that we are not short selling. In cases some of them are negative and obviously some of them would be positive, these weights of x, which means I am trying to basically utilize some stocks which I do not owe, sell it and give it in the market to someone, utilize that money from selling that stocks or scripts which I do not own, and basically utilize that money in trying to basically jack up the total amount of investment which I have for those stocks which are already with me, and I think that they will give such higher returns. So, in this model we have two equations which are not robust and they contain terms which are not robust and they contain terms which have uncertain parameters, but we will try to basically ignore them accordingly. We need to convert them, these two constraints, to the robust counterparts in order to accomplish that we propose the particular theorem. Now, and the fact is that whenever you are trying to basically solve the concept of robustness, they would be either less than type and greater than type depending on the returns being greater than RP and the risk being less than equal to sigma p. So, what we will try to do is that we will try to basically convert them using the plus and minus some concept of perturbation which is there and convert them into robust counterpart, and that we will basically see in the later part as we solve the problems accordingly. With this part, I will basically end the 59th lecture and basically continue giving a discussion on the robust counterpart in the last lecture, which is the 60th one. Have a nice day and thank you very much.